Hello everyone, my name is Sabdika Kimire and I am presenting my final project for ISAT 6900 class instructed by Dr. Yoshida. Moving forward, the project title is Application of Fast Fourier Transform in Brain Tumor Detection using MRI Images, and I am doing this project under the guidance of Dr. Sommerfeld and Dr. Blanchard. Okay, first let's discuss about the project overview. Why FFT in brain tumor MRI images? The primary objective of doing this project is to enhance the accuracy and efficiency of brain tumor detection using MRI image by utilizing Fourier transform for frequency domain analysis. Fourier transform the image from spatial domain to the frequency domain. Low frequency capture major features such as tumor, and high frequency often represent noise or fine details irrelevant to tumor detection. And the main benefit is noise reduction and feature extraction. High frequency noise can be filtered out, enabling focus to shift to relevant tumor features and identify tumor areas and improve the accuracy. This is the process flow diagram for this entire project implementation and analysis. Firstly, I extract the dataset from Kaggle and implement the original MRI brain image in the model. The accuracy was 55% without applying FFT and any kind of filter. Then, firstly, I load MRI images and split dataset to training and testing set and applied normal 2D FFT along with low pass filter, removing the high frequency component, and reconstructed the image by applying inverse FFT and implement the reconstructed image in model which improved the accuracy to 62.50%. After that, I explore on different kinds of FFT like Windowed FFT, zero padded FFT, but I apply Windowed FFT to improve the accuracy in tumor detection along with low pass filter and reconstructed the images using inverse FFT, and while implementing the model the accuracy was upgraded to 66.50%. And this is the overall project flow diagram for implementing FFT and doing the analysis. Okay, let's discuss on how I apply 2D FFT and low pass filter. For the entire project, I use a Python library. Firstly, I load the image and set up input and output folder, convert the image to grayscale for preprocessing, and apply 2D FFT to shift the frequency domain and center the low frequency component, and max low frequency components by removing high frequency by setting them to 0 and cutoff size to 30 to retain only low frequency component, removing noise and irrelevant details. After that, I work on inverse FFT and reconstructed the filter image to highlight tumor related features. Then, as mentioned earlier, I use that output images for model implementation, and the accuracy was improved to 62.50% after removing the high frequency component. And this is the output images after applying FFT and low pass filter for removing high frequency. And why I use low pass filter? Low pass filter removes the high frequency noises, making the image clearer and enhancing the visibility of tumor, and it enhances the tumor boundaries. The main thing I prefer is artifact removal. It eliminates the high frequency artifacts caused by machine imperfection or patient movement, making the image more accurate. And low pass filter play a critical role in improving the image processing, leading to better detection of tumor. The first image is original MRI image, and I applied FFT to this original image, and this is FFT magnitude spectrum. The spatial domain image is converted to frequency domain. Then I removed the high frequency component and reconstructed the image applying inverse FFT. This is the result after applying FFT and low pass filter. The tumor region seems more clearer as the noise are removed. In previous slide, I show you the result after implementing FFT and low pass filter, but I explore on a high pass filter as well, but I didn't find the high pass filter applicable in tumor detection because we can see the output. There is no any features of tumor by applying high pass filter and FFT. So we didn't prefer a high pass filter in tumor detection as it causes loss of tumor features leading to loss of important tumor details and making it harder to identifying them. Similarly, it increases the noise and artifacts. High pass filtering may enhance small irrelevant details or noise which can confuse the model or observer, making it more difficult to detect the tumor accurately. After working on with high pass filter, low pass filter and doing spectrum analysis, I read some research paper and found out that Windows FFT is more better than normal FFT in tumor detection as it reduces the spectral leakage. Firstly, let's discuss what is Windows FFT. Windows FFT involves applying windowing function like hamming or handing and other different technique to an image before performing FFT. This helps reduce edge discontinuities, focusing on relevant frequency component and improving the FFT result while minimizing the noise. Okay, what is Hamming window? Hamming window is a type of windowing function used in signal processing to reduce spectral leakage when applying a Fourier transform to a signal or images, but I use Hamming window in image in this project. We can use in any signal and it is defined mathematically as this. This function is equals to 0.54 minus 0.46 cos 2 pi n by n minus 1, where Wn is the weight or value applied to the nth pixel of image and n is the total number of pixels in the image and small n is the index for the pixel position within the image ranging from 0 to n minus 1, and this function smoothly reduces the values at the edges of image, tapering them to 0, reducing high frequency noise when transforming the image into the frequency domain. Okay, Okay, let's see the result after applying Windows FFT, normal FFT and low pass filter. As I have discussed about Windows FFT in detail in earlier slide, I have implemented Windows FFT and this is the magnitude spectrum after applying Windows FFT. We can compare the image and see the differences, and after applying low pass filter and reconstructing the images after applying inverse FFT, the tumor region is more focused, other components are removed from the images in compared to normal FFT. We can see lots of image and features in normal FFT output image, but the tumor region is focused and seen clearly in Windows FFT. Okay, after visualizing the result, let's discuss about impact of Windows FFT with Hamming in brain tumor detection. Windows FFT reduces the spectral leakage. In brain MRI image, spectral leakage refers to spreading of frequency component caused by transitions such as boundary of image. This causes distortion in the frequency domain and cause impact to distinguish the tumor's edges clearly. Windows FFT reduces this distortion, providing more clear representation of tumor features, and spectral leakage happens when sharp edges in the image cause high frequency noise to spread across the frequency spectrum, and this windowing function smooths the image's edges, minimizing this leakage and allowing for clearer and more precise tumor boundaries. Also, Windows FFT improves the tumor detection, enhancing the visibility of tumor features by suppressing high frequency noise and focusing on the relevant frequency associated with the tumor. So Windows FFT with Hamming makes very high impact in tumor detection. After experimenting on normal FFT, windowed FFT, high pass filter, low pass filter, and analyzing the spectrum, I work with model implementation. Firstly, as I mentioned earlier, I worked in implementing model in original MRI image. The accuracy was 55%. After that, I applied normal FFT and low pass filter, and the accuracy was improved to 62.50%. Then at last I apply Windows FFT and low pass filter, and the accuracy was improved to 66.25%. So to conclude that, as I mentioned earlier, original image without FFT have 55% accuracy. Normal FFT plus low pass filter have 62.50 accuracy, improving tumor detection. And Windows FFT Hamming window function plus low pass filter improve the accuracy to 66.25% by reducing the spectral leakage, enhancing the frequency representation, and improving tumor detection. Spectral analysis for tumor detection involves converting MRI images into frequency domain using FFT, followed by manipulation of high pass and low pass filter to enhance relevant features and reduce noise in frequency domain. To conclude, the combination of Windows FFT and low pass filtering significantly improves tumor detection accuracy, leading to more reliable and precise results in MRI analysis. And these are the references I used during the implementation of Fourier transform in brain tumor detection. I extract the model from Hugging Face and read this research paper to explore more on the Fourier transform in brain tumor analysis. Okay, this is all about the implementation of Fourier transform in brain tumor detection. Please let me know if you have any questions or suggestion on this project. Thank you.